G'day team, and welcome back to yet again another video on the introduction to calculus. We've been doing a bit of work with gradients and calculating gradients of different things in different ways between 2 points instantaneously, the gradient of a tangent at a specific point. We even started to look at the idea of limits. Now, you might be wondering where all this is leading to, and it's a really good question. So what we're actually going to look at is finding the derivative function, which is also known as a gradient function, but we're going to stick with derivative function. And it's going to be able to tell us the slope or the gradient of a curve at any given point we choose. So instead of going through this really long process of having to find the gradient and pick 2 points on my tangent and go through all that, we can find this general derivative function of my original function, which allows me to substitute in an x value and find the gradient of that tangent. So if I have a function y, which is equal to f of x, is called, so the derivative function, and we want to call and label it f prime of x or f dash of x. Now, all f dash of x represents is my gradient at a specific point. So we've got my dy, which represents the change in y, so my rise, and my dx is my change in x, which is my run. So f dash of x is rise over run, or y2 take y1 over x2 take x1. Now typically, if my functions in terms of f of x, I use f dash of x. But if my function's given to me in terms of y, I typically use dy by dx. But just know they mean the exact same thing. Now you're probably wondering, how do we use it? Where do we get it from? So a little example of how to use it. Now, I've got a function here, f of x equals x squared. Now, just take with a grain of salt for now that the derivative function, f dash of x squared is equal to 2x. So if I wanted to find the gradient at x equals 4, so if I graphed x squared, looks something a little bit nice quick sketch. We know it looks something really ugly, but like that. So if I wanted to find at, say, 4, I would have had to draw a tangent and find the slope of that little tangent there. But what I can do with my derivative function is substitute in the x value, so 4, so 2 times 4, the slope or gradient of that tangent at 4 is 8. It's as easy as that. Now we've got to discover a way of finding this derivative function. So one thing I want to make really clear, f of x, okay, my function f of x gives me my y coordinate, f dash of x gives me my gradient. I just want to make that super duper clear. So let's just have a little bit of a practice with this new notation. So for the given graph, find f dash of 3. Now this just means the gradient at x equals 3. Now x equals 3 is here, so I've drawn in a tangent. We need to pick 2 points. I've got 1 and 0, so that's the point down here. And I've been given the point 5 and 8, so 5 and 8. Now, gradient of a straight line, super duper easy. y2 take y1 over x2 take x1, 8 on 4, which is 2. So f dash of 3 is equal to 2. Now, I don't want to be sitting there for every single point calculating this gradient and this gradient and this gradient down here or this one here. I want a nice simple way that I can substitute these values in. So in the last video, I showed you this diagram here, and we looked at finding the derivative or the gradient at A, and we looked at moving this B value down my curve closer to A to make this gradient between A and B closer to this tangent. And we did that by making H smaller, and that's where we got into limits. So to actually find this moving gradient as B gets closer to A and H is getting smaller, we use this equation here. So the derivative at a specific point is f prime of A, f dash of A, is the limit as h goes to 0, so as h gets really, really, really small, of f of a plus h minus f of a all over h. So we've seen that little part before, rise over run. Now that's great for a specific point, but what if we want to know the whole function? Well, in that case, we replace our little a's with our general x. Now, this diagram hasn't really changed all that much. I've just changed my little a's to x's as a general x. So, in my formula, the only thing I change is my little a's to x. So my derivative function, or the derivative f dash of x or dy by dx, is the limit as h tends to 0 of f of x plus h, which is a composite function, minus f of x all over h. So this formula here is going to be used quite a lot. Now, this process is known as differentiating from first principles. Finding the derivative is known as differentiating, okay? And first principles means using this formula here. So, with that formula, let's find a derivative function. So, given f of x equals x cubed, let's find our derivative function. Now, I've got my formula here. I know f of x, that's my x cubed. So let's write that over here. So f of x equals x cubed. Now that's given to me. But I don't know f of x plus h. Now h itself is just a general placeholder, but we need my function in terms of x plus h. So if I bring that down here, f of x plus h, everywhere I see an x in my function f of x, I need to replace with x plus h. So this becomes x plus h cubed, okay? Now, if I had, for example, a plus 2x on the end as well, I would have to go 2x plus h. So it has to go in for all of my x's. Now, we're not doing that just yet, but just as a little side note, it must go into every x in my function. All right, let's substitute in what we have. So every time we do a new line, we have to write the limit as h tends to 0 until we apply the limit. So f of x plus h is x plus h cubed minus, and I want you to get in the habit of putting my f of x in brackets. That way, if I have multiple terms, the negative is known to go to both. And we're going to divide that by h. Now, if I'm looking at applying my limit, if I put h equals 0, oh, that's undefined, so we can't do that. So we need to play around and manipulate the top a little bit. Now that cubic there, x plus h cubed, we can expand using a binomial expansion. So I've got x cubed plus 3x squared h plus 3xh squared plus h cubed. And then I've got minus x cubed left over on the end here, all over h still. Now, hopefully on the top line, you can see I've got x cubed minus x cubed, and they cancel out. Now, at this point, you should hopefully notice that everything without a h in the top line has cancelled out. So all of these terms remaining will have some h in it. And what that means we can do is we can take out h as a common factor on the top. So h, the first term I'm left with 3x squared, then I'm left with 3x h plus h squared, all over still h. Now I've got h on the top, h on the bottom, they cancel out. So I'm just left with the limit as h tends to 0 of 3x squared plus 3xh plus h squared. Now if I apply my limit, nothing becomes undefined, so I can do my substitution. So 3x squared plus 3x times by 0 plus 0 squared, that just gives me 3x squared. So my derivative, f prime of x equals 3x squared. So if I wanted to find the gradient at, say, x equals 3, That means f prime of 3 is 3 times by 3 squared, which is 27. So the gradient of the tangent to x equals 3 is 27. It's a bit of a long process, but it's quite beautiful. Just be super duper careful when we're doing our subtracting our f of x. Use brackets. Use your little check that after cancelling out, everything should have a h in it. Hopefully this has been helpful, and we'll show you a neat little trick in the next video. So stay tuned, and we'll see you then.